Thank you all for coming, and thank you to Altium for having me. I think this is one of the first presentations at AltiumLive on power electronics, so hopefully you guys will learn something new today. And then one quick point, if you guys could hold your questions until the end, that would be much appreciated. I just want to make sure that I can get through all my material in the allotted 45 minutes. All right, so let's start off with an easy question. I expect everyone's hands to be raised for this one. So how many of you have released the magic smoke when you've been testing your electronics? All right. So pretty close to everyone. So how many of you have captured the magic smoke? This will answer how many power electronic engineers are in the room. Does anyone recognize this picture? Okay. By show of hands, how many people have had this happen to them before? Okay, great. So this is a actual picture of a IGBT module that I exploded in my experimentation. Inside these IGBT modules, there's a silicon gel that's used for insulation, and it also is used to prevent moisture and debris, but it also works remarkably well for freezing explosions in time. So you can pretty much see the point at which the die explodes and the magic smoke trying to escape. So why am I showing you these pictures? Well, power electronics, it's hard. You're switching very high voltages and high currents at very high frequencies, and it can lead to countless headaches if you don't know what you're doing. So a well-designed PCB will provide the best efficiency and lowest noise possible, but on the other hand, poor PCB layout can lead to EMI issues, component stress, and poor efficiency. So today I'm going to present 3 ways, not 5, as it says in the schedule. 5 is too much content for 45 minutes, so I'm just going to do 3 ways to what's that? Yeah. So 3 ways to improve the layout of your power electronics to maximize efficiency, EMC, and reliability, and not release the magic smoke. So in order to set the stage, I'm going to give you a brief overview of power electronics and the market trends we're seeing. And then, formatting. Then we're going to cover high voltage isolation, gate drive layout, and then minimizing loop inductance and parasitic capacitance. All right, so let's get started here. So let's start with the basics in case you aren't familiar with the field. What is power electronics? So power electronics is the application of power semiconductors to control and convert electricity from one form to another. So you can do AC to DC, DC to AC, DC to DC, and AC to AC. My particular expertise is in inverter and DC-DC converter design, and these are some boards we have developed. So figure 2 shows a silicon carbide half bridge, which is an essential building block in 3-phase inverters and buck converters. This is a 1 kilowatt AC to AC converter, and this is a relatively higher power 120 kilowatt quad IGBT inverter. So this last one here it's used for controlling 4 motors. Oops. So power electronics is a field that's constantly evolving. The trends of power electronics are depicted by this upside down pyramid. And the industry wants higher power density, higher efficiency, and lower cost. Well, how do you get that? So most of the innovation that occurs is driven by breakthroughs in semiconductor materials. So first it was the thyristor or SCR, then it was power MOSFETs and BJTs, then it was the IGBT, and now we're in the middle of another paradigm shift to silicon carbide and gallium nitride wide bandgap devices. So these new materials are enabling higher power density, higher efficiency converters, but they come with a number of challenges, but that's for another presentation. So this is a very popular field right now. It's a crucial element in electrified vehicles and renewable energy generation. And it's not just in automotive, but in all forms of transportation. So electrification is happening with planes, scooters, trucks, boats, you name it. Not only that, but power electronics are also needed to interface renewable energy generation methods such as solar and wind with the grid. So it's a great time to be in the field, and there's lots of opportunity going on. All right, so now that you have a good idea of what power electronics is and where the market is, let's jump into high voltage isolation. So to start, I want to show you a quick clip of a lightning storm filmed at 100,000 frames per second. Pretty cool video. So the question I want you to think about are, why do lightning strikes to ground occur? So I'm not a meteorologist, so I'm going to explain this in simple electrical engineering terms. And so lightning strikes to ground occur because when there is a potential difference between the cloud and the ground that exceeds the breakdown voltage of air, the air ionizes and a path is formed for hundreds of thousands of amps to flow. So why am I talking about lightning? Well, the same thing can happen on a PCB if you don't have enough spacing between nodes with a high potential difference between them. The air or the PCB dielectric can break down and arcing can occur. Okay, so my goal with this section is to teach you how to provide sufficient spacing to prevent arcing from occurring through air or across the PCB. So generally, if your product exceeds 60 volts DC, you should be diligent about high voltage spacing in your design. So when it comes to spacing, there are two important terms to understand, clearance and creepage. So clearance is the direct distance through air between two conductors, and creepage is the distance along the PCB between the two conductors. So clearance is measured through air, so there's not much that can be done at a layout level to reduce the required spacing besides careful placement of your circuit or your circuit components, and then also using insulating materials. So it's usually best to separate your low voltage and high voltage sections of your board if possible. Creepage requirements depend on a number of variables, including the working voltage, pollution degree, and then the type of isolation that's required. So working voltage is pretty self-explanatory. That's the voltage between the two conductors of interest. Pollution degree is the amount of dust, moisture, or particulate in the air around the PCB. And then for insulation types, this includes functional, basic, double, supplementary, and reinforced. So there are a number of standards that attempt to define creepage requirements for PCB design. The two that I think are the most well-known are IPC 2221A and UL 60950-1. So both provide clearance tables based on peak voltages. The UL standard provides much more detail in terms of pollution degree, insulation type, and required isolation distances. But ultimately, the standard that you should apply depends on the standard that your project must conform to. So for the sake of simplicity, we're just going to look at the IPC standard for this presentation. It's a lot easier to digest, and in general, this standard provides isolation distances that are much larger than the minimum required. So if your design is done according to the IPC standard, it can be safely assumed that adequate isolation has been provided. Okay, so I pulled this table straight out of the IPC documentation, and it shows electrical conductor spacing as a function of working voltage and then the circuit conditions. So as you go down the table, working voltage increases, and then each column describes a set of conditions. So for example, B2 is external conductors that are uncoated, operating in an environment at elevations from sea level to 10,000 feet. And then for voltages greater than 500 volts, you need to add this per volt value to the previous row spacing. So let's do an example. So let's say we have a pretty standard application, a 2-layer board that is uncoated that will operate at sea level with a 400 volt DC bus. So first we need to find the voltage range we're operating in. So 400 volts is in between 300 and 500. And for the environmental conditions, we said they're external conductors that are uncoated at sea level. That corresponds to B2. So we see that we need 2.5 millimeters of spacing. Great. So now I'm going to show you a video of me going over how to implement this clearance rule in Altium. So in almost all automotive and aerospace applications, you need spacing between your high voltage and low voltage sections of your circuit. So that's what I'm going to show you in this video. Let's see if this works here. Perfect. Okay, so the first thing I'm going to do is put a blanket around all the nets that are in the low voltage section of the circuit. And then I create another blanket for the high voltage section of the circuit. And then I'm going to put a net class indicator here, or net class parameter. So I'll title that LV to indicate low voltage. And then I'll do the same thing for the high voltage section, title this HV. So then I'm going to update my PCB. So then I'm going to go to my design rules and create a new clearance rule. And I'm going to define the clearance between these two net classes. So I'll select the first object to be net class HV, second object will be net class LV, and then I'll put in my 2.5 millimeters of spacing. So and then I have my clearance visible to ensure I did everything correctly. And as you can see, it creates a bubble around the opposite net class, and it'll make your route 2.5 millimeters away from any node that belongs to that net class. So this is a great tool that can be used in any design where you have a large potential difference between nodes and you need to find the spacing between them. Okay, so in summary, make sure to pay attention to what standards your project must conform to, and then figure out what spacing you need based on this, and then use net classes, blankets, and clearance rules to implement this in Altium. All right, so the next thing we're going to talk about is our gate drivers. So if you don't know what a gate driver is, it's very simple. It's a circuit that's used to turn a power semiconductor, such as a MOSFET or IGBT, on and off. So in essence, it's really just an amplifier. It takes a PWM signal from could be a microcontroller unit, and then amplifies it to the gate voltages required by the MOSFET or IGBT. And in addition, it also amplifies the sink source current capability because microcontrollers can only drive a few milliamps, and the peak currents required by these power semiconductors can be several amps, so you need to amplify the current as well. We'll talk more on this later. So most gate drivers for motor drive applications feature isolation between the control signal pins and the driving circuit. And this allows individual circuits to possess different ground potentials. And this is essential if you're designing any circuit with half bridges where the source of the top switch is connected to the switch node. Signals can still pass back and forth between the isolation barrier via optical or capacitive or inductive methods. And like I said before, this galvanic isolation is required in almost all automotive and aerospace applications to prevent shock hazard. So let's take a quick step back and examine how to turn a MOSFET on. It may seem simple, but I'm going to try to explain it in terms that will help us build a foundation so we can better design our layout. All right, so the gate of a MOSFET can be modeled as a capacitor. And you have two control handles with this when it comes to the gate, the voltage and the current. So the voltage applied between the gate and the source determines the drain current. And these two parameters are related by the transconductance, and that can be seen in this plot right here. So VT is the threshold voltage, the minimum voltage that's needed to turn the MOSFET on. Usually this is around 2 to 4 volts. But the manufacturer will usually recommend a gate voltage to use. And this is, for power electronics, it's usually 10 to 20 volts for MOSFETs. And anything over this can actually damage the switch. So you want a high gate voltage, but not too high. So the gate capacitor, it cannot change its voltage instantaneously. So it has a non-zero finite switching interval, and how fast you can get charge in and out of that gate ultimately determines the switching time. And this is called the gate driver's drive strength. Okay, so now I want to take a look at a very simple gate driver circuit. So this one has no protection features besides the isolation barrier. So its job is twofold, and that's to amplify the PWM inputs to the gate voltages desired by the MOSFET, which in this case is plus 15 volts and minus 3 volts. And then the second job is to source and sink high currents to turn the MOSFET on and off very quickly. So just so you guys know what's going on here, U1 is an isolated gate driver power supply, and it supplies the voltages needed to drive the MOSFET. In this case, plus 15 to turn it on and minus 3 to turn it off. U2 is this gate driver IC. It's used to separate or isolate the control signals from the driving circuit. We have a RC filter because these PWM lines are high impedance and they're typically pretty long, so they can pick up stray fields, and the RC filter helps to attenuate that. These bypass capacitors can be thought of as a charge source, so during a switching interval, charge is transferred from these capacitors to the gate of the MOSFET. And then the last thing here is this path right here. And so the peak current can be solved for using Ohm's law. It's just delta V over R. So our delta V in this case is plus 15 minus 3 over our gate resistance, and that's the peak current. And this is the path that we're going to focus on because this is the most important path when it comes to the layout of our gate driver. All right, so let's talk about parasitic inductance in the gate drive loop. So inductance is proportional to loop area, and long traces and large loops can lead to longer switching times, which will increase the switching loss and reduce efficiency. And if the inductance is high enough, you can get ringing in the gate source waveform, which can reduce the lifetime of the MOSFET and potentially lead to circuit failure. And of course, this will also lead to EMI radiation. So to wrap that up, the gate source inductance leads to longer switching times, ringing, and in turn, higher component stress and potential failure. Okay, so let me take a sip of water. I want to take a look at an example of bad gate drive layout. So what's shown here is the first inverter that I ever designed. And the gate drive board is this black board, and it's driving a IGBT module. So the gate signal and the return path have to go down through these headers, across the board, and then to the gate and the source pins on the IGBT module. So the inductance, the loop area is very large, and when we measured it, it was 200 nanohenries. And we saw the effects of this on our gate source switching waveform, and you can see the large voltage overshoot at turn on and turn off. Like I mentioned before, this can lead to increased component stress, EMI production, and potentially component failure. So in the second iteration of the design, we solve this by placing the gate driver right on the PCB that is directly connected to the power module. And each driver circuit was located as close to the gate and the source pins as possible, and the loop area was very tight. And as a result, the inductance was 4 nanohenries as opposed to 200 nanohenries, a factor of 50 reduction.
Just a little bit.
Yeah. Okay. Yep. So you can see that the overshoot and the ringing was completely eliminated just by changing the layout. Okay, so now I want to take a quick look at another example, but from a layer-by-layer view. So just so we're clear what's going on, these are the MOSFET pins. The gate is right here. The source is right here. This is the gate resistor. This is the gate drive IC. And this is the gate drive power supply. And you can see the layout is all, it's very tight. It's all on one layer, which is important to reduce loop area. And this is an example of good gate drive layout. Okay, so in summary, significant inductance in the gate drive circuit can lead to voltage overshoot and ringing, which can lead to increased component stress, EMI, and potentially circuit failure. So to mitigate this, the gate driver should be located as close to the gate of the power transistor as possible, and the loop area should be minimized to keep inductance down. Okay, but what's even more important than the gate loop is the high-frequency power loop, and this is the next thing we're going to discuss. So the high-frequency power loop is the path between the DC link capacitor and the power semiconductor switches. So this is the loop that does all the heavy lifting. It's switching high currents and high voltages at very high frequencies. And in electrical engineering, you need two things for a resonance to occur, inductance and capacitance. And so every conductor has parasitic resistance and stray inductance, and every semiconductor in its off state exhibits some sort of output capacitance. Now these values are very small. I mean, we're talking picofarads and nanohenries, but when you're switching at 10 kilovolts per microsecond, that's enough to excite these parasitic resonance circuits and cause oscillatory behavior. So the number one thing that you need to look out for is voltage overshoot. So you need to ensure that this does not exceed the breakdown voltage of the device. And this voltage overshoot manifests itself when one MOSFET is turned on while the other MOSFET's body diode is conducting freewheeling current. like when you're in the dead time period of a switching cycle. So it's important to understand this, so we're going to go through it state by state quick. So let's say we have a synchronous buck converter operating at an arbitrary duty ratio with an inserted dead time to prevent shoot-through. And in state 1, we're going to assume that the low side switch is closed. So current is flowing through the load and the low side switch. So state 2, the low side switch opens. And because this inductor is stiff, current must continue to flow. So it'll flow through the MOSFET's intrinsic body diode. So once that dead time period ends, the high side switch closes. And at this moment, there's effectively a short circuit because of this reverse recovery charge of this body diode. And that net forward current is equal to this link current minus this freewheeling current, because this must still continue to flow because it's stiff. So that excitation is equal to this. And then once the reverse recovery period of that diode ends, this low side switch presents a capacitive load to the circuit, and your RLC circuit's formed. So the R is the on-state resistance of this top MOSFET. The L is the summation of the inductances in your high-frequency power loop. So this includes the ESL, the inductance in the connections between your DC link capacitor and your power semiconductors, and then also the inductance in the actual leads of the power semiconductors as well. And then the C is the output capacitance of this low side switch. So from this, we can form an equivalent circuit that we can use to analyze the behavior of the RLC circuit. And we'll see that it exhibits a classic second-order response. And in this, we're plotting the normalized capacitor voltage versus natural frequency. And we're plotting it for different damping ratios. So the equation for damping ratio is shown here. It's R over 2 times the square root of C over L. And in power electronics, we want this R to be as small as possible because our conduction losses are proportional to R. And if we want to maximize efficiency, we want to keep this as low as possible. The C is fixed. This is our output capacitance of the switch. And then, so really the only handle that we can change is this L, and that's our DC link inductance. And so how do we do that? We pretty much apply the same principles that we applied to the gate source loop inductance. So big thing is the loop area needs to be minimized. So the DC link connections should be planar laminated bus bars or PCBs that are sandwiched together. Ideally, you should use high-frequency film capacitors with a low equivalent series inductance. And they should try to be located as close to the pins of the power terminal as possible. And then if you really want to optimize this, you can use a multi-physics program such as COMSOL to analyze the high-frequency current paths and maximize magnetic field cancellation. So Wolfspeed did a study on this, and their bus bars for this inverter are shown here. And that's, if you want to look at this paper, it's in the references. You can go to my presentation after the fact and take a look at that. Okay, so the last thing I want to discuss is parasitic capacitance. And the foundational equation that you need to remember for this one is the one that you're taught in Circuits 101. I is equal to C dV dt. So the induced current in two nodes is equal to the capacitance between them times the rate at which you're switching voltage. So you have to be extremely careful with the routing of your switch node and everything around it. Like I said before, you could be switching at 10 kilovolts per microsecond or higher. And if you just have a couple picofarads of capacitance, you can get pretty large displacement currents. And that can lead to a lot of noise that your circuit has to contend with. So this PCB is an example of really bad layout. So all these nodes are connected to a switch node. This is the plane that these switch nodes are referencing. And so you can see all these parallel plate capacitors between the traces and the planes. And you'll get a lot of induced currents in these nodes. And for this particular design, the noise ended up showing up in our gate driver circuit, and it led to a lot of issues. Okay, so to wrap this up, let's go over 3 key takeaways of the presentation. So the first takeaway pertains to high voltage isolation. So pay attention to the standards that your project must adhere to. And then to implement the isolation requirements in Altium, use net classes and clearance rules. The second takeaway, gate drive layout. So the gate driver should be located as close to the gate of the power transistor as possible. And that's because inductance is proportional to the gate loop. So this also needs to be minimized. And a low inductance design will generally reduce overshoot and ringing and improve switching times. The third takeaway pertains to DC-link parasitic inductance and then parasitic capacitance. So there's a large surge current because of that reverse recovery charge associated with the MOSFET body diode. And then this can excite the parasitic RLC circuit in your high-frequency power loop, and that can ultimately lead to overshoot and ringing across your devices. So to mitigate this, high-frequency DC-link film capacitors should be used, and they should be located as close to the power terminals as possible. For the DC-link connections, you should try to use laminated bus bar, or if you're using a PCB, use power planes with that are on adjacent layers. So like layers 1 and 2 or something like that. And then when it comes to parasitic capacitance, you need to be very careful with the routing of your switch node. So the dVdt is very high, and that can induce large displacement currents in sensitive nodes, even if there's just picofarads of capacitance between them. So these are the references for my presentation. And yeah, that's all I have for you. I'll take any questions at this time.
Okay, I'll walk the mic over because we need to have these on the recording.
Hi, so with respect to the isolation that you talked about earlier, the IPC standards and stuff, do you know if Altium takes into account the isolation in the Z direction between, I know it's going to depend on the dielectrics of the board, but from one layer to another, that sort of isolation as opposed to just X, Y in a plane?
I don't know for certain, but I don't think it does. What's that? Oh, yeah. So that's another thing is that, in the lecture this morning, they said they're going to have something about creepage in 20. So that whole first section could be obsoleted with Altium 20.
Mine is not a question, it's only an observation.
Yeah.
You were using IPC and also the UL, which is also for European, is the CUL.
Mm-hmm.
Okay, if you're gonna be certifying any product, go by the standard of the agencies who certifies the product, because they will check the creepage and clearance,
Mm-hmm.
and they will go by the table, not by the IPC.
Okay, yeah, just pay attention to the standards that your project needs to conform to.
So during one of the presenter outside I was discussing, they were suggesting to make capacitance using PCB layers.
Sorry, I can't hear you. Can you speak up?
So I was speaking to somebody in the outside presenters, and they were discussing about making a capacitance decoupling caps using the PCB layers.
Mm.
Can you talk more about that?
I've thought about that, but I don't know. It seems pretty unpredictable, but it's possible. You could do it. not sure.
Do you have some specific strategies that you use in order to minimize the capacitance in your traces, like what you talked about in the very last portion of your presentation?
Yeah. So ideally, you want to avoid, so these are parallel plate capacitors. When there's a trace going over a plane, there's capacitance between them. So yeah, make sure that like any node that is switching at a very high DVDT, make sure that whatever it's referencing isn't underneath or above that switch node.
So at that point, you would cut away the plane from under your trace.
Yeah, right.
If you do that without controlling the return path, you're going to get expansion of fields, though, and that could lead to other problems. So wouldn't you need a coplanar return path, for example, if you cut away the planes?
Yeah.
Just a comment, and maybe Rick can answer this, but what about a hatched plane?
That would help. That would lower the capacity, still give you a return path.
Thank you.
Same subject. Would that be a good case for a dedicated return path, not using a plane for the return path? Have an adjacent trace, or is that going to have? Would that reduce the capacitance? Treat it like a differential pair.
Yeah, I think so.
Treat it as a differential trace. That would make sense.
There's a bird that just flew in.
So I've got a question about the actual layout. I presume you're doing your own layout and creating those design rules?
Yeah.
You showed a bubble when you went to route. How exactly do you get that to turn on in Altium?
It's in the, yeah, so it's in the PCB settings.
Boundary clearances.
Yeah.
Go to the settings, turn on boundary clearances.
Right. Yeah, I could show you after. It's hard to describe like up here without Altium in front of me.
We have 5 more minutes. Anybody else have questions? Raise your hand. I know he's being upstaged by a bird.
Could you just briefly mention the last 2 ways that you didn't include? You did 3 instead of 5. Can you just briefly state what the other 2 are?
Well, so I had parasitic inductance and parasitic capacitance split up. And so that was another way. And then I was going to do thermals as well. And because I just wasn't able to fit all that content in the 45-minute period, and so I cut 2 of the ways and then consolidated the parasitic capacitance and inductance section.
Anyone else? I'm talking to Bruce. What's going on?
This is actually more of a comment to a previous question than a question itself. You're talking about, or asking about in-plane capacitance between 2 different layers of the board. For most power electronic applications, that's probably not feasible. The voltages between the 2 layers would have to be much too high for the thin layer that you'd need to get any meaningful amount of capacitance. So it's good for microprocessors and things, but not for power electronics.
Okay, anyone else? Okay, oh, we do. Wonderful.
What's the edge time on your switching nodes?
The edge time?
Yeah, the edge time.
You mean like the rise time?
Yeah.
It's in the order of a couple of nanoseconds. He mentioned that it's, what, 10,000 volts per microsecond?
Yeah, that was
That works out to about 10 volts per nanosecond, which gives you a rise time of probably on the order of a nanosecond or two.
Yeah, yeah. I mean, yeah, it's usually anywhere from 5 to 20 nanoseconds.
Oh, it's that high. Okay.
Depending on what gate resistance you use, but yeah, it can get pretty low.
Yeah, and when you talked about controlling parasitic inductance and capacitance, the best way to do that, of course, is with length, because we discussed using coplanar traces to lower capacitance, but that's going to raise inductance, right? So whatever you do, you're kind of, it's one thing or the other, and the best way, and I'm sure you would agree, to control all that is to keep length short.
Yeah, absolutely.
I'll get one over here.
So do you have any thoughts about putting a series resistance between your gate drive to the MOSFET, a compromise between EMI and switching losses, or?
Yeah, I think you should always include a footprint for a gate resistor. But yeah, you want to minimize it as much as you can to decrease your switching loss, but of course, that's going to lead to more EMI. So there's a trade-off there between switching loss and EMI, so you got to balance that.
When you're lower EMI, you tend to kill efficiency, right?
Yes. Yes.
You talked about thermal management. Is there any tool in Altium that provides us thermal management? Like we know these plates are getting this much heat generation in it, and then we can like estimate.
Is there any tool in Altium that provides thermal management?
Or like COMSOL, do you use COMSOL? How do you do that?
I'm honestly not too familiar with COMSOL. I just read that paper that said that that's what they used for the analyzing the high frequency current paths. I imagine it could be, but sorry, what was that?
I think SolidWorks provide FlowTerm, which we can, I don't know, somehow interface Altium to SolidWorks and that.
Yeah, ANSYS has some products too. Yeah, my partners have just used ANSYS for that stuff.
I think ANSYS has IcePack, which is
right. Yeah, exactly.
This will be our last question here.
All right, to answer your question, I think Altium has the PDN analyzer. I think it's doing thermal. If they're not already, I know it's in the plans. My question for you, a lot of power design circuits use gate drive transformers. So you have the gate driver, then you've got a transformer, and then you've got the switching device, the silicon. And obviously you want to minimize loop inductance and parasitics along the entire path. But is there a preferred, is it better to have the gate drive transformer closer to the gate drive IC or closer to the transistors?
So the gate drive transformer is used for amplifying the gate voltage?
Sometimes it's one-to-one.
Or is
it's mostly there for isolation.
Isolation. Oh, I see. I've never done that in my designs before, so I don't have experience on that. Yeah, I mainly just use gate driver ICs that have isolation built in. But if it's more cost effective to do it like that, I could understand why you'd go that route. So fortunately, I don't have a great answer for you.
Okay, I think we should give Jason, thank him so much for this presentation.